Hello everyone, today we're going to be going over section 2 part A from the 2023 AP Calculus AB FRQ section. This is going to be 2 questions. You're given 30 minutes to solve these 2 questions and a graphing calculator is allowed. For this review, I'm going to be using the TI-84 plus CE. So let's just go over these 2 questions. So question number 1 says, a customer at a gas station is pumping gasoline into a gas tank. The rate of flow of gasoline is modeled by a differentiable function f, where f of t is measured in gallons per second, and t is measured in seconds since pumping began. Selected values of f of t are given in the table, right? So what does this mean? This means that we have a function f of t, and f of t is gonna pretty much be this graph, and it's gonna compare seconds or time, which is our x-axis, so seconds. And it's going to tell us how many gallons we pumped into a gas tank, right? So our y-axis is going to be gallons, 2 L's, gallons in gas tank. And I don't know why I put gas with 2 S's, but gas tank. Right? So, and we know this because it's measured in gallons per second. So each second, which is our x-axis, we're going to have a certain amount of gallons pumping in. And you can see here, we can roughly sketch that it's increasing, right? So we start at 0, 0, we end at... or rather, gallons per second is our slope. So at 0, our slope is 0. Then at 60 seconds, let's say that's here, our slope is 0.1. So our slope is increasing, decreasing, and then flat out, right? But what it's going to tell you is that at 60 seconds, there's this amount of gallons in that gas tank, so on and so forth, right? So that's what the graph is going to somewhat look like, and that's what it's going to represent. So part A says, using correct units, interpret the meaning of the integral from 60 to 135 of f of t in the context of the problem. Right? So that's the first part. And the second part says use a right-Riemann sum with 3 subintervals to approximate the value of this integral, right? So the first thing they want to know is they want to test this if we know what an integral is. So what an integral from 60 to 135 is going to do is it's going to tell us the area underneath this curve from starting from 60 and ending at 135 seconds. So what is the area? And I'll put it in green, but it's going to ask us, or it's going to tell us, the integral is going to tell us this area underneath this graph over here. Now, in order for us to interpret the meaning of it in the context, we need to know what that integral is actually going to represent, right? And for people who are comfortable with this topic, you know that it's just going to represent gallons, right? But for people who aren't comfortable with this and people who might be confused by this, I like to think of the integral as like a time traveling machine, right? An integral makes you go back in time, right? So and it makes you remove 1 unit of time from the unit of measure, right? And what I mean by this is and this is something that we all learned when we were learning motion, right? We learned about acceleration, or a of t. We learned about velocity, v of t, and we learned about distance, d of t. And we learned that these 3 are connected because the integral of acceleration is equal to velocity, and the integral of velocity is equal to distance, right? And if you notice something, the units for acceleration is usually going to be meters per second squared, or some unit of measure per second squared. And then when you integrate that, you get velocity. And velocity, the unit for velocity is going to be meters per second. And if you integrate velocity, right, you put the integral sign in front of velocity, you're going to get distance, and the unit for distance is meters. So every single time I attach this magical symbol over here, this integral sign, look what's happening to my seconds. It's going down by 1. Here I had meters per second squared. Here I have meters per second to the power of 1. Here I have meters per second to the power of 0, right? So it's going back in time. It's removing the unit of measure by 1. So if I find the integral of f of t, follow my rule here. Remove the seconds, right? Remove 1 from the second. Meters per second, that's gallons per second, that's gallons per second to the power of 1, right? If you integrate this, you're going back in time. It's going to be gallons, right? So you know that the unit is going to be gallons, and it's just going to tell you the amount of gallons of gasoline which was pumped into the tank from 60 seconds to 135 seconds, right? So the hardest part here is interpreting what the actual unit is. But then you're just going to say that because this is in gallons per second, right? This is the slope. You go back in time 1, you get gallons, and you're just going to say that this is going to represent the amount of gallons which were pumped into the tank from 60 to 135 seconds. So it's going to represent the total amount of gallons of gas pumped into the tank from t equals 60 seconds to t equals 135 seconds. All right, now for the second part of this question, it's asking us to use a right-Riemann sum with 3 subintervals to approximate the value of this, right? And that's why they gave us this table, right? So if we're going to be using a right-Riemann sum in this context, we are going to use it with 3 subintervals. And if you don't know what a right-Riemann sum is, or what a Riemann sum in general is, I'll go ahead and I'll quickly review that right here. So if we have this function, for example, right, let's just call this f of t, this function right here, and we want to estimate the area underneath this curve. One way we can do it is by splitting this curve into rectangles, right? So we can split it once here, and we can split it once here, and then we can split it once here, right? So we split this into two rectangles given these 2 points, right? Point 1 and point 2. And then what I can do here is, because I split them up, I can just draw an imaginary rectangle up here and multiply the distance from this point to this point by the distance from this point to this point, right? And I could do the same thing here. I can go and multiply the distance from this point to this point by the distance to this point to this point. And then I can add them up and I get a general area or a general feel for the area underneath the curve, right? And what a right Riemann sum specifically is it says that I'm going to take this point specifically, and I'm going to use the height of this to multiply it by the base. And then I'm going to use this point and use its height to multiply it by this base, right? And what a left Riemann sum would look like is something else. A left Riemann sum would say, I want to take the leftmost point and use it as my height. And then I want to use the leftmost point and use it as my height, right? And notice how this is going to give you a different area. If I use this point as my height for this distance, I get a much smaller rectangle. But if I use a right Riemann sum and I use the point to the right, I get a much bigger rectangle that's being formed, right? So my point is they're using a right Riemann sum, which means that I'm going to multiply the distance between the intervals. So I'm going to multiply delta x, which is going to be how much x changes, or the distance between the intervals. And I'm going to multiply that by f of the right value, right? So for the interval from 60 to 90, right, how much space is there from 60 to 90? How much does x have to change to go from 60 to 90? It's going to change by 30, right? So for my first interval, the first rectangle I'm making, I'm multiplying 30 by f of the right value, right? So in this interval, my rightmost value is going to be 90. So f of 90 is 0.15. So I'm going to multiply 30 by 0.15, right? And that's my first subinterval. That's my first rectangle that I just calculated. Then I'm going to add that to my second interval, right? From 90 to 120. How much do I have to change my x to go from 90 to 120? By 30. So then I'm going to multiply that by 30 times my rightmost value, f of my rightmost value, which is 120. F of 120 is 0.1. It's 30 times 0.1. Then I'm going to add that to my last interval. And here we're going from 120 to 135. That's going to be plus 15. So my x changed by 15, so my delta x is 15, and now I need to multiply this by my rightmost value, which is going to be f of 135, which is 0.05. And my right Riemann sum is going to equal to the sum of that, right? So how can I express this as an answer? All you have to do is do the following, right? I can just write that the Riemann sum, the integral from 60 to 135 of f of t dt is estimated to be 30 times 0.15 plus 30 times 0.1 plus 15 times 0.05. And I can say that that's roughly equal to, and I'll just plug those values into my calculator, and I'll get that when you add all these up, you get 8.25 gallons. And make sure to include the unit, and boom, that's full credit. That is full credit of part A, right? So now part B says, must there exist a value of C from 60 to 60 is less than C, which is less than 120, such that f of C is equal to 0, right? Or the f prime of C is equal to 0. And we'll get into what this means. I'm just going to go ahead. I'm going to erase my work from here so that we have more space to work with. I'm going to erase it up here as well. So what this question is asking us is it's really testing us if we know the mean value theorem. And what the mean value theorem is going to say is if you have this curve or this function right here, right? And if you have a starting point, let's say a starting point A, we'll put that down here. And you have an endpoint B, and I'll put endpoint B right here. What it says is that if you take the slope of the line that that passes these 2 points, right? If you take the slope of this line, or find the slope between A and B, which that line is going to look something like this. That's the line that crosses both of them. Then, assuming that the function is continuous and differentiable, right? So by continuous, we mean there's no gaps, there's no pauses, there's no spaces. All of these points are defined and real. And differentiable, meaning that I can find the slope of each one of these points, right? So if it's continuous and differentiable over the interval a comma b, right? So including these 2 points, then there's going to be some value in between a, b. So there's going to be some value that's in between a and b, where the slope is going to equal that slope between a, b, or f prime of x, or f prime of c is equal to the slope from a to b. So f of a minus f of b over a minus b. And I'll just draw that out. So we have the slope passing through these 2 lines. And if you kind of look here, you can kind of see that if I draw a line through, I don't know, maybe this point, which is we'll call C, that line is going to be parallel to this line, right? That line that I just drew through this point, that slope is going to equal to the slope of this, right? So if the function is continuous and differentiable over AB, then there's going to be a value between AB, which is what this means, such that if I find the slope that passes through this point, C, it's going to equal to the slope of the line that passes through A and B, right? That's all we need to know here. So let's see if this is true. So from 60 to 120, if I want to find the slope of the line that passes through these 2 points, I'm going to have to take f of 60 minus f of 120 and divide it by 60 minus 120. So what's that going to look like? F of 60, I know f of 60 is 0.1. So I have 0.1 minus f of 120, which is also 0.1, divided by 60 minus 120, which is negative 60, right? So this is going to equal to 0 because 0.1 minus 0.1 is equal to 0. So the slope of this line from A to B is going to equal to 0. And now it's saying that for a point C, right, the slope through the point C is also equal to 0. So is this true? Well, yeah, it is going to be true, right? F prime of C, which is just taking the slope of the line that passes through C, is going to have to equal to 0 because C exists between these 2 intervals, and because the average rate of change, or the line that passes through these points, is 0, right? And we know this is true because this is a differentiable function. Anything that's differentiable is also continuous. So it passes the criteria for the mean value theorem. So in order to earn full points for this, we're going to have to state that that f of t is differentiable over 60 to 120 and is continuous on 60 to 120, right? So it's differentiable and it's continuous on the interval from 60 to 120, right? That's the first thing. We proved this. Then we need to state that given 60 is less than C, which is less than 120, there must, right? So we're agreeing there must be a value C such that f prime of C equals 0, since f of 60 minus f of 120 divided by 60 minus 120 is equal to 0. And then we need to state that we're citing the mean value theorem. So we're going to say by MVT, or we're going to do these 3 dots, MVT, or you can just say by mean value theorem. And that's how you earn full points on this part, right? So you need to state the mean value theorem. And now we can move on to part C, right? So what is part C going to say? And I'm going to erase my work up here. So part C is going to tell us that the rate of flow of gasoline in gallons per second can be modeled by the function g of t is equal to this big jumble of numbers. So for for t, which is greater than 0 but less than 150 seconds, using the model, find the average rate of flow of gasoline over this interval, right? So the average rate of flow from this to this. And we have to show the setup for our calculations. So when we're talking about the average rate of a function or the average of a function, really it's asking us to find the integral from a to b, right, of that function, in this case f of t. And then it's going to ask us to multiply that integral by 1 over b minus a. And it's going to give us the average value. Here it's asking us for the average rate of flow, aka the average value of this function. So all we're really going to have to do is set our bounds. Here it says from 0 to 150, so I know that my a is going to equal to 0, my b is going to equal to 150. So when I write my work and I set up my calculations, all I have to do is 1 over 150 minus 0 of the integral from 0 to 150 of g of t dt. That's all. Make sure you match it up, and then I could just draw an arrow and simplify this to 150 from 0 to 150 of g of t dt. And then because it's a calculator section, you don't need to show your work, and you just need to show that it equals to whatever that equals to. And we're going to go ahead and we're going to put this into our graphing calculator and evaluate it. And my answer is going to be 0.09599. So the average rate of flow of gasoline over the time interval is going to equal to whatever value I just got, so 0.095. That's it. And you could round your answer if you want. So now we're moving on to part D, which is the last part of this question. It's going to ask us, using the model of G defined in part C. So we're going to be using this function that they gave us. Find the value of G prime of 140 and interpret the meaning of your answer in the context of the problem, right? So it's going to ask us to differentiate this or find the derivative of this and then plug 140 into that derivative. Now, thankfully, this is the calculator section, so you don't actually need to derive this at all. You don't need to do that by hand. Plug it into your calculator. But you do need to show that you're finding the derivative. So what I would do in this case is I would write just d dt of g of t, right? Or g of, in this case, 140, right? G 140 is going to equal to, and then just plug that into your calculator. So over here, I have the function. If you go into math and you go into 8, you're going to find your derivative function, and you're differentiating this, and you're just going to type in your function, x, and then here we have 500 cosine of x over 120 squared, close that parentheses, close this parentheses, and you're going to put your x as 140, right? And you're going to get your answer to be negative 0.0049. So this is going to equal to negative 0.0049. And now we have to find our units, right? So how do we interpret this in terms of the function, right? How we can do this, and also, by the way, instead of doing ddt, you don't even need to show your work that much. You could just state that, I guess I was doing too much there, but you could also just state that g prime of 140 is equal to that. You don't even need to show that you differentiated in terms of t of g of 140, right? All you need to, because they don't even ask you to find, if they don't ask you to show work, you don't need to show work. So you could just say that g prime of 140 is equal to that. That's how you find it. Now we have to interpret the meaning in your answers in the context of the problem, right? So remember how I was talking about how the integral goes back in time, right? Or it removes the per time. Now the derivative is going to go forward in time, or it's going to add a new time. And what I mean by this is you have, let's just say that you have d of t, which is going to be your distance. Then you have v of t, which is your velocity, and then you have a of t, which is your acceleration, right? D of t, the units is going to be meters, v of t is meters per second, and a of t is meters per second squared. Now, if I find the derivative of distance, I'm going to get velocity, and velocity's units is meters per second squared. sorry, meters per second. Then if I find the derivative of velocity, I get acceleration. And the units for acceleration is meters per second squared. So notice every single time I go ddx of this function, I'm adding meters per second to the power of 0, right? Anything to the power of 0 is equal to 1, and meters over 1 is just equal to meters, right? So I'm adding 1 to the time, right? So I differentiate v of t, and I'm going from meters per second to meters per second squared, right? So I'm adding time. So really, f of t, if I were to differentiate this, is actually just going to be gallons per second squared, or gals second squared. If you don't like to think that way, we're finding the slope of the slope. So we're really finding the rate of change of the rate of change. If this is how many gallons are flowing in to the gas tank every second, I want to know how quickly that rate is changing, right? And if our rate is negative, that means that the rate at which gallons are pouring into the tank is decreasing. So it's going to be negative 0.049 gallons per second squared, right? And that's going to give us the point for the unit, right? And now we need to interpret this, and we're going to say that this means that the rate at which gallons are flowing into the tank is decreasing by 0.0049 gallons per second every second. And that's going to be the proper interpretation of that. And that's going to be problem number 1 done, right? Number 2 says that Steven swims back and forth in a straight path in a 50-meter long pool for 90 seconds. His velocity is modeled by v of t is equal to this big function, where t is measured in seconds and v of t is measured in meters per second. Okay. Find all times t in the interval at which Steven changes directions. Give a reason for your answer, right? So I'm going to write A, and then we're going to solve this, right? So when they ask us when someone changes directions, they're really asking us, when does v of t change signs, right? Notice that v of t is going to represent velocity. And when velocity is positive, you're going to the right. And when v of t is negative, you're going to the left, right? And that sign is going to tell you, that sign change is going to tell you whether you're going to the right or going to the left. So really all we need to do is plug this function into our graphing calculator, and we need to see at which points v of t is going to change from positive to negative. We're going to our calculator and we're going to graph this, right? So I'm going to go into y equals, and I'm going to write 2.38 e to the power of negative 0.02x. And I'm going to multiply that by sine of pi over 56 t, or in this case x, right? And I'm going to go ahead, I'm going to hit graph. And we're going to get this graph, and obviously we're going from 0 to 90. So I'm going to set my window. I'm going to write my x minimum as 90 and my x maximum, my x min as 0 and my x max is 90, right? So we're going from 0 to 190. And you can see here that our graph is going to be positive, so his velocity is going to be positive. Remember that this graph, this equation is going to give us his velocity. So his speed is positive, he's traveling to the right. And then you can see around this point, somewhere around here, around 50, all of a sudden, his velocity starts to become negative, or he changes directions. So I'm going to have to find that point. I'm going to have to go to second, trace, and I'm going to find the 0, right? So my left bound is going to be here, and then my right bound is going to be some random point after his speed is negative, right? So here his velocity is negative. I'm going to go ahead, I'm going to press that. And it says that the 0 happens at x equals 56, right? So I'm going to write that down. So I know that 56 seconds. So what happens at 56 seconds? Let's go into our table. So I'm going to go into table set, and I'm going to make our table start at 56. And then I'm going to go into my table. So you can see here that at 56, his velocity is equal to 0. So really, v of 56 is equal to 0. What happens before 56? His velocity is positive, and after 56, his velocity is negative. So he changes directions from left to right at 56 seconds, right? And there's going to be no other time where he changes directions because on the graph, we didn't see any other times where this graph changed from positive to negative aside from that point 56, right? So here, we're going to say that at 56 seconds, Steven's speed, or not his speed, but Steven's velocity is 0 meters per second. In other words, v of 56 is equal to 0. And then what we're going to have to say is we're going to say that he changes directions at 56 seconds because his speed from 0 to 56, and we're just going to put a table here. We're going to do a sign table because v of t changes signs from positive to negative at t equals 56 seconds. That's all, right? So we just need to say that there's a sign change at 56 seconds, which means that he's going from right to left. That's all. So for part B, it's going to say find Steven's acceleration at time equals t equals 60, right? So show the setup for your calculations and indicate units of measure. Is Steven speeding up or slowing down at time t is equal to 60, right? So his acceleration, remember I was talking about this in the last time. Distance, if you differentiate distance, you find the derivative of distance, you're going to get velocity, right? And then if you find the derivative of velocity, you're going to get acceleration, right? So this is already our velocity. So what we need to do is we need to differentiate this for x is equal to 60 seconds. That's all, right? And we need to state in our answer, we need to state that that velocity is equal to acceleration, right? So we know that v prime of 60, which is another way of writing the derivative of this function at 60 seconds, is going to equal to our acceleration at 60 seconds, right? So then we have to say that a of 60 is equal to what? And we'll go ahead and we'll calculate that right now. All you have to do is go into math, press 8, ddx, and instead of typing this entire function out into here, because we already wrote it up here, what we can do is we can go into our calculator, press vars, yvars, function, y1, and then press x equals 60. Calculate that. And what y1 does is it copy and pastes anything that you put into y1 into there, right? So it saves time. And it's going to say that his acceleration at 60 seconds is negative 0.03601. So I'm going to write that this is equal to units meters per second squared. So that's the first part, right? We found his acceleration and we proved that why that's his acceleration. Now we're going to need to tell him if he's speeding up or slowing down at t equals 60, right? And this what matters here is if he's going is the direction he's going in, right? So really his velocity is decreasing by 0.061 meters per second every second. But if his velocity is already negative, right? So if his v of t is like negative 30, and every second it's decreasing by negative 0.03, that means that his velocity is speeding up, right? Because if you subtract a number from a negative number, right? If you from 30, you subtract 3, you're going to get negative 33, right? So if his speed was positive, and every second he was increasing his speed by negative 0.03, 30 minus 3, or 30 plus negative 3 is going to equal to 30 minus 3, right? And this is our acceleration. So if his velocity is positive and his acceleration is negative, that means he's slowing down. If his velocity is positive and his acceleration is positive, he's speeding up, right? So when the signs match, you speed up. And when the signs don't match, you're slowing down. So let's see if the signs match or not. So here we're going to go into our table, and we're going to scroll down to x equals 60. And we see that x equals 60, our velocity is negative, right? So that means that he's speeding up by 0.0316 meters per second every second, and we can see here that our velocity is still increasing. That just means he's going to the left. So we need to say that his speed, or rather we could just say that he is speeding up at t equals 60 because the velocity his velocity and acceleration are both negative at t equals 60 seconds. That's all. Because if the signs match, that means that you're going up. If the signs don't match, that means you're going down. All right, part C, and I'm going to go ahead, I'm going to erase everything that I wrote about up here as well. All right, almost done, guys. So if we look at part C, it's going to say, find the distance between Steven's position at t equals 20 and his position at t equals 80 seconds. Find the setup for your calculations, right? So the distance between his time at t20 and t equals 80, what this sounds like to me is just the integral from 20 to 80 of whatever this is, v of t dt. And that's it. That's all you need to do here. It's a pretty simple question. Set up the integral and show the setup for your calculations. All you have to do is just, you have to say that, hey, if I'm finding the distance, I'm integrating from 0 to 80, the function vt dt. And I have to write that this is equal to whatever it's equal to, right? I'll go into my calculator. I'll go into math, press 9 to get to integral function. I'm integrating from 20 to 180, right? That's what they asked me. Nope, from 20 to just 80. And then the function that I'm integrating is just going to be the function that I typed into y1, right? This is y1. I typed a function here. This is going to copy and paste that function into here. And this is going to be in respect to x. It's going to tell us that the area under the curve from 20 to 80 is going to be 23.38. So v of t, the integral for v of t dt is going to be 23.38 meters. So the distance, and we have to state that the distance Steven swam from t equals 20 seconds to t equals 80 seconds was 23.38 meters. Right? And if you're confused about this, just remember that if you find the integral of velocity, you get distance. And specifically, you're going to get the distance between point A and point B. That's all. So D says, find the total distance, and this is very important. Find the total distance Steven swims over the interval is greater than 0, but less than 90 seconds, and show the setup for your calculations. So here, we're finding the total distance, right? Which means that generally when we calculate when we calculate position, right, it's going to be the difference. So what I mean by this is if, for example, I was running forward for this long, and then all of a sudden I decided to turn around at this point, right? At this specific point, I decided I'm going to start running back. Here, my v of t was positive because I'm going to the right, and here my v of t is negative. And if I want to find my position, I'm going to have to take this positive side, right? And I'm going to have to subtract it to this negative distance. And this position is going to tell me only from here to here. It's going to tell me that my position changed by this much. It's not going to tell me it changed by this much, right? Because I went back. But if it asks me for the total distance that I walked, it means that I'm going to have to add this positive to this negative, or to the absolute value of this negative. So instead of subtracting the negative distance I walked, I'm going to have to add it over, right? And in other words, I'm going to have to find the absolute value because this value is negative. Absolute value of a negative is going to be a positive, right? And because I have two positive values, they actually combine into one instead of being subtracted from one another. So if I want to set up my calculations, all I have to say is the following. All I have to say is that I'm integrating from 0 to 90 the absolute value of v of t in respect to dt. That's all. Find the total distance he swims. Total distance is going to be the absolute value, right? Go into my calculator and plug this in. I'm going to have to go into math 9 to get my integral. I'm finding the integral from 0 to 90. I'll go into math. I'll press this button right here to get into number. I'm going to press enter for my absolute value. Then I'm going to copy and paste whatever I put into my y1 into here. And I'm going to put dx. And this is going to calculate, and it's going to tell me that his total distance traveled was 62.164 meters. So, and this is equal to 62.164 meters. And then I have to state this, that the total distance Stephen traveled over the interval 0 greater than or equal to t, which is greater than or equal to 90 seconds, is 62.164 meters. Right, and that's part D. That's all you need to know. If you have any questions, please leave them in the comment section below. I know this is a pretty wordy explanation, but I really wanted to cover every base. I think these responses would have earned you full points. If you have anything, let me know in the comments. Otherwise, hope you learned something. Have a nice night.